Last part, we learned about the derivation of Michaelis-Menten equation. Okay, and what it is, we already know. It's described the rate of a monosubstrate reaction. So, in this part, first we learn about the Leuwenhoek-Bark equation. So, what is Leuwenhoek-Bark equation? Okay, basically it's a further derivation from the Michaelis-Menten equation. So now, if you ask me, why we need this, okay, I'll talk about this, but first I'll talk about how Lee and Weaver derive, these two scientists, Lee and Weaver Park, they further derive the Michaelis-Menten equation. Okay, so the Michaelis-Menten equation can be algebraically transformed into equations that are more useful in plotting experimental data. Okay, so I mean if we consider the Leeuwenhoek-Bark equation is just a simplified, okay, or algebraically transformed form of the Michaelis-Menten equation, but this equation is more useful than the original Michaelis-Menten equation in plotting experimental data. Okay, so one common transformation is derived simply by taking the reciprocal of both sides of the Michaelis-Menten equation. That means just inverse the equation. So this was the original Michaelis-Menten equation, right? V is equal to V max substrate concentration divided by Km plus substrate concentration. So if you just reciprocate it, that means inverse it, finally it becomes like this: 1 by Vz equal to Km by Vmax into substrate concentration plus 1 by Vmax. So if you plot this in the graph, it will look like this. The original Michaelis-Menten equation looked like this hyperbola, but this derivation, that means the line we were Bark derivation, it becomes a straight line. So why it's become a straight line? Because this one, 1 by Vz equal to Km by Vmax substrate concentration plus 1 by Vmax, it's a straight line equation, right? What was the straight line equation? Y equal to mx plus c. It looks like that, right? Y equal to mx plus c. So this is a equation. This is a straight line equation. So that's why if we plot in the graph, in x-axis we take the 1 by substrate concentration, and in y-axis we put the 1 by v0, then it will give a straight line. Okay, so what we understand from this graph? So this form, that means the Line-Weaver-Bark equation is called the okay, so is this form of the Michaelis-Menten equation is called the Line-Weaver-Bark equation. That means the straight line equation. Okay, so for the enzymes who obey the Michaelis-Menten relationship, a plot of 1 by V0 versus 1 by V0 versus 1 by S, okay, which is the double reciprocal of V0 versus S plot. Okay, so here's a straight line. It's a equation of a straight line. That's why it's become the straight line. Okay, so and this straight line has a slope of Km by Va Vmax and intercept of 1 by Vmax. Okay, on the intercept of 1 by Vmax on the 1 by V0 axis here. Okay, and an intercept of 1 by Km on the 1 by S axis here. Okay, this is 1 by S axis here, the intercept. So the double reciprocal representation is also called Line-Weaver-Bark plot. You already know that has the great advantage of allowing a more accurate determination of Vmax, okay, which can only be approximated from a single plot of V0 versus substrate concentration. Okay, so the double reciprocal plot of enzyme reaction rates is very useful in distinguishing between certain types of enzymatic reaction mechanisms and in analyzing enzyme inhibitions. Okay, so I just in the beginning I told you that why this Line-Weaver-Bark equation necessary. Okay, so what is the use of this kind of equation, such as the Michaelis-Menten one or this one? We need the equation to study enzyme, their kinetics, right? To determine or calculate their Vmax, V0, that means the rate of the equation. Okay, so we can do that by using Michaelis-Menten equation. Definitely we can do that. But if we think practically, the Lineweaver-Burke equation, it gives a straight line. So practically, I mean, if we think practically, dealing with a straight line is much more easier than dealing with the hyperbola. Okay, so that means this equation is, I mean, if we use this equation, it will be more efficient for us to study the kinetics or determine the kinetics or rate of a reaction. Okay, so we are done with the Michaelis-Menten equation and its further derivations like Lineweaver-Burke equation. So now, to understand the kinetics, we need to understand some more parameters, or more, we have to be familiar with some more uh, constants. Okay, so one constant is dissociation constant. We already know about the Km, the Michaelis-Menten constant. There are some other constant too, like dissociation constant and then catalysis constant. Okay, we'll learn about this first, the dissociation constant. Okay, so now we know, okay, the Km, that means the Michaelis-Menten constant, can vary greatly from enzyme to enzyme and for different substrates of the same enzyme. Okay, I mean, two different enzyme, they can have the different Km, and also the same enzyme catalyzing different substrates can have different Km. Okay, so the actual meaning of Km depends on specific aspects of the reaction mechanism, such as the number and relative rates of the individual step of that reaction. Okay, so Km is the concentration of substrates when the reaction reaches half of Vmax. We already saw that. Okay, so now a small Km value indicates high affinity, since it means the reaction can reach half of Vmax in a small number of substrate concentration, right? Because if Km is half of the Vmax, then that means if Km is small, so what we understand by the value of Km? So for example, if the value of Km is small, what we understand by from it? We understand that, okay, I mean, if the value of Km is very low, I mean, is small or low, it indicates that the enzyme has high affinity with the substrate. Okay, that means the rate of the reaction will be high and Vmax will be achieved much quicker. Okay, so this that means if the Km value is smaller, then the Vk, I mean, if the Km value is smaller, it means the reaction rate will be faster. So that means Vmax will be achieved quicker. But and in the contrary, if Km value is high, that means the enzyme has less affinity for the substrate. So the rate of the reaction will be slow. So Vmax will be achieved slowly. Okay. So now, for a two-step reactions like uh, the which reaction, this one, okay, this is a two-step reaction. So for a two-step reactions, we already know that Km equal to K1, K minus 1 plus K2 divided K1. We already know this, right? We know this from when we derived the Michaelis-Menten equation. Okay, so now when K2 is rate limiting, okay, so for this two-step reaction, when K2 is rate limiting, that means K2 is is smaller than the K minus 1, and Km reduces to K minus 1 by K1. Okay, because K2 is, as K2 is very low, we can neglect it. So that's why the Km become this. I mean, Km become to Km equal. I mean, it becomes that Km will be equal to K minus 1 by K1, because as Km is very low, we can neglect it. Okay, so this term is called the dissociation constant. Okay, Kd. Okay, so where these conditions hold, Km does represent a measure of the affinity of the enzyme for its substrate in the ES complex. So what we understand by this line, I mean, what we understand by Km? I mean, what is the meaning of Km? Km represents a measure of the affinity of the enzyme for its substrate. I mean, by the value of Km, we can understand that what is the affinity of the enzyme for the substrate in that reaction. Okay. However, I mean, if the scenario is different, for example, this scenario does not apply for most enzymes. Okay, because sometimes K2 is much greater than K minus 1, then Km becomes K2 by K1. Okay, so that means this scenario that Km represent the affinity of enzyme for a substrate only apply when K2 is much smaller than K minus 1. So if the opposite is true, that if K2 is greater than K minus 1, we cannot understand or define the Km value in this way. Okay. So it was about the dissociation constant. Now the catalysis constant. Okay, another constant. Okay, again, think about this reaction: enzyme plus substrate, ES, then EP, then E plus P. Okay. Now, if an enzyme reacts by the two-step Michaelis-Menten equation, I mean, when we derive the Michaelis-Menten equation, we consider the one step, right? I mean, this step was not there. ES, E plus S, ES, then E plus P. Okay, this step was not there. So if the reaction has a additional step, which is called a two-step Michaelis-Menten equation, and if the K2 is rate limiting, then Vmax will be K2 ET. Okay, so now when the product release step, that is breakdown of EP into E plus P, is rate limiting, most of the enzyme is in the EP form at saturation. That means at when this step will be the rate limiting. So that means most of the enzyme will be not, I mean, free, will be not in the ES but in the EP form, and in that case Vmax can be represented by this equation. Vmax will be K3 into ET. Okay, so now so from this we understand that the value of Vmax actually depend on the step. Which step? Which step is the rate limiting step of the reaction? Okay. Okay. Now here's come the catalysis constant, which is represented by kcat. Kcat means catalysis constant. So when we use the catalysis constant, that is kcat, is used to describe the limiting rate of any enzyme catalyzed reaction at saturation. Okay, so if the reaction has several steps and one is clearly rate limiting, kcat is equivalent to the rate constant for that rate limiting step. Okay, so now for example, if we say that for this reaction, this is the rate limiting step, in that case the value of kcat will be same as the value of K3. That means kcat will be K3. Okay, so in this case the constant kcat is a first order rate constant, and so thus it has units of reciprocal time. Kcat is also called turnover number. Okay, it is equivalent to the number of substrate molecules converted to product in a given unit of time on a single enzyme molecule when the enzyme is saturated with substrate. That means by kcat is also represent that how much substrate, how much product will be produced in a certain amount of time. Okay, so that's why it is called turnover number. Okay, so now in the Michaelis-Menten equation, kcat equal to Vmax by Et. Why? Because I mean we already know that if for this reaction this step is the rate limiting, kcat will be K3. Okay, so in that case the Vmax will be K3 E3. I mean when for this reaction, if this step is the rate limiting step, Vmax equal to K3 Et, and we just saw that for this case K3 kcat will be equal to K3, so Vmax become kcat into Et, right? Vmax will be kcat into Et, so that means kcat will be Vmax by Et. Okay, in that case we can rewrite the Michaelis-Menten equation in this way. Okay, V0 will be K cat ETS divided Km plus S, because the original Michaelis-Menten equation was V0 equal to Vmax S divided Km S. Okay, so we just substituted the Vmax value here. Okay. However, this was when one step is clearly rate limiting. What happens if there are multiple rate limiting steps? That means several steps of the reaction is partially rate limiting. In that case, kcat becomes complex. Okay, it becomes a complex function of several of the rate constants that define each individual reaction step. Okay, so now what is the use of kcat and km? Okay, that's the, I mean, we learn what is km and what is kcat, but what is their use? Okay, what is the significance of kcat and km? So the significance is that we can use this to compare catalytic mechanisms and efficiencies of different enzymes. Okay, so the kinetic parameters kcat and km are useful for the study and comparison of different enzymes, whether their reaction mechanisms are simple or complex. Okay, we can compare among or between different enzymes. Okay, so now each each enzyme has values of kcat and km that reflect the cellular environment, the concentration of substrate normally encountered in vivo by the enzyme. Okay, and the chemistry of the reaction being catalyzed. Okay, so that means from kcat and km we can understand this. What is the cellular environment? Okay, the concentration of the substrate in the in vivo system and the chemistry of the reaction. Okay, this value also allow us to evaluate the kinetic efficiency of enzymes. Okay, now however, although these parameters, that means kcat and km, allow us to evaluate the kinetic efficiency of the enzymes, but either parameter alone is not sufficient. That means we cannot evaluate the kinetic efficiency only by the kcat or by the km. Okay, because two enzymes catalyzing different reactions may have the same kcat. I mean, why only kcat or only km is not sufficient enough? Because two enzymes catalyzing different reactions may have the same kcat, that is the turnover number. Okay, yet the rates of the uncatalyzed reactions may be different, and thus the rate enhancements brought about by the enzymes may differ greatly. Okay, so experimentally, the Km for an enzyme tends to be similar to the cellular concentration of its substrate. So an enzyme that acts on a substrate present at a very low concentration in the cell usually has a lower Km. It's understanding, right? So if an enzyme's concentration is very low, what that mean? Definitely its Km will be lower, because low Km means this enzyme has high affinity for the substrate. Okay, that's why we don't need, I mean, like, suppose you are studying an enzyme and you found that its cellular concentration is very low. That means its affinity is very high. So that's why much enzyme is not needed for the reaction. Okay. Okay. Now, okay. Now, if you think that what happened if the Km value is higher? So, if a enzyme's Km value is higher, much substrate will be there. So, as we just learned, that kcat and Km alone is not sufficient enough to uh, evaluate the kinetic efficiency of enzymes. How we can do that? So the best way to compare the catalytic efficiencies of different enzymes or the turnover of different substrates by the same enzymes is to compare the ratio kcat by km. Okay, and this ratio is called a specificity constant. That means a specificity constant is the ratio between kcat by kn. That means a specificity constant is equal to kcat by kn. Okay. Okay. So now when the substrate concentration is much lower than the kn, so the equation that we saw here, V0 kcat ETS divided km by S. Okay. it reduces or transforms into this form, V is equal to k cat by km ETS. Why? We just said that substrate concentration is much lower than the km. That means we can ignore that one. Okay, we can ignore the substrate concentration. So that means if we ignore the substrate concentration, it becomes this k cat by km Et into S. Okay. So now for this equation, V0 in this case depends on the concentration of two reactants, the Et and S. Although E is the enzyme, we can consider it as a substrate, right? Because the substrate and enzyme is reacting. That means both are regarded as substrate. So, and from this equation we can know that, I mean, K cat is the constant, Km is also constant. Who are the variables? These two. Enzyme concentration and substrate concentration. These two are the variables. That's why, that means the value of V0 will depend on this, on substrate, on concentration of these two. Okay, so that's why it is this equation is a second order rate equation, because the rate depend on the concentration of two substrate. Okay, and as it's a second order rate equation, the constant k cat by km is a second order rate constant, and its units is per m per s. Okay, now there is an upper limit to k cat by km, okay, imposed by the rate at which enzyme and substrate can diffuse together in an aqueous solution. Okay, and this diffusion control limit is 10 to the power 8 to 10 to the power 9 per mole per second. Okay, and usually many enzymes have a k cat by km near this range. I mean 10 to the power 8 to 10 to the power 9. Okay, and such enzymes are said to have achieved catalytic perfection. I mean, if an enzyme has a k cat by km value near this two, I mean k cat by km value near this range 10 to the power 8 to 10 to the power 9, we can say that that enzyme has high catalytic efficiency. Okay. So now, as we already know the equation, I think we can solve some math. Okay, so there is a math here. So I'll just give you a brief, but I'll suggest you try this at your home. Okay, so now think about a scenario. I mean, okay, solving math is not difficult. So what is important if we want to solve a math? The first thing is we need to understand the equations. So if you understand the equations, solving a math is not difficult. Okay. Okay. So let's try to get it. So consider this scenario. This is a reaction. Okay, enzyme catalyzed reaction. So from sad, happy, form. Okay. So a team of motivated researchers set out to study the enzyme, okay, who is they call happiest. So what's the function of this enzyme? They transform sad into happy. Okay, and these researchers who was studying with this equation, they find that the k cat for happiest enzyme is 600 per second, and they carry out several additional experiments. Okay, so now when et the okay when concentration of Et is equal to 20 nanometer and concentration of SAD, that means substrate is 20 micromolar, and the reaction velocity V0 is 9.6 micromolar per second, calculate the K. So this is the problem. So how we can solve that? To solve it, we need to have the equation. Okay. So we already know that the equation is this. V is equal to k cat ETS divided km by S. We already know that, right? So we have to find out whether we have the value of this one. So what is our target? What was our question? They asked us to calculate the km. So if we have to calculate the km, we need the value of the other parameters. So are all the parameters given there? V0 is there, concentration of SAD is there, concentration of ET is there. Okay, everything is there. Okay, so what we need, and also the value of k cat is there. So what we need, if we just put the value of all these variables here will be km, and if we calculate, finally we'll get the value of the Km. Okay? It's not that difficult. We just have to use the equation, and from the question we have to find the value of the different variables of that equation, the parameters of that equation. So if you understand this math, please practice this math at your home. Okay, so thank you, see you in the next lecture.